Right. The problem with studying distortion, though, is that it takes a really long time. Fabricating the lenses that you need to study the problem can take weeks or months, and once you have them, you still have a long process of building a functional display system with them. So to address that, what the team did was they built a distortion simulator that uses virtual objects and eye tracking to replicate the distortion you would see for a headset for a given optics design and display it using 3D TV technology. So this allows the team to study different optical designs and distortion correction algorithms without needing to build an actual headset. With this unique rapid prototyping capability, the team has been able to explore dynamic distortion correction in literally minutes rather than months.
Yeah, so that's a big improvement. Eye tracking is also an underappreciated technology for virtual and augmented reality, and it's how the system knows what to focus on, how to correct optical distortions, and which parts of the image it should devote more resources to rendering in full detail. And that last part really matters because the thermal and power envelopes for a smaller headset are so constrained for wearable devices that you're always trying to squeeze every last bit of performance out of the system, and if you can just render the parts that you're focused on in the most detail while having the periphery be in lower resolution like the physical human visual system, then that's potentially a very important optimization. So that brings us to the last major frontier in display technology, and this is a big one too. Because while resolution, varifocal, and distortion all make a meaningful contribution to realism, arguably the most important dimension of all is high dynamic range, or HDR. Basically, it's the overall brightness and contrast of a display. Because our experience is that when lights are bright, you see colors pop and shadows are dark, and then that's when the scenes really start to feel alive. But the issue today is that the vividness of screens that we have now compared to what your eye sees in the physical world is off by an order of magnitude or more. So let's get into this in a bit more detail.
So the key metric for HDR is nits, or how bright the display is. And research has shown that the preferred number for peak brightness on a TV is 10,000 nits. And the TV industry has made progress in introducing HDR displays that move in that direction, going from a few hundred nits to a peak of a few thousand today. But in VR, the maximum nit level right now is about 100 on Quest 2. And getting beyond that with a form factor that's wearable is a big challenge.
Yeah, so we're going to need to get to significantly higher brightness levels than what we refer to as HDR on traditional screens today. And then, of course, the challenge is we need to do that in something that is battery-powered and comfortable to wear. So, to try to figure out the best path forward, our display systems research team built this prototype, or I guess this is a part of the prototype, that basically puts an incredibly bright lamp behind the LCD panels. And this one's pretty heavy, so we have these handles so you can hold it like that. But as far as we know, this is the first HDR VR system, and internally we call it Starburst. It's, to be clear, wildly impractical in this first generation for anything that you'd actually ship in a product, but we're using it to test and for further studies so we can get a sense of what the experience feels like. And the goal of all this work is to identify which technical paths are going to allow us to meaningfully improve in ways that start to approach the visual realism that we need. And if we can make enough progress on retinal resolution, and if we can build proper systems for focal depth, and if we can reduce optical distortion and dramatically increase vividness, then we have a real shot overall at creating displays that can do justice to all the beauty and complexity of physical environments. But it's going to take a bunch of iterations on each of these technologies to get there, and then we have to integrate them all together. So we're also looking at some further out solutions that could enable us to take big leaps forward. And at the same time, we're working on how to package all these different technologies into smaller, lighter, and ultimately affordable headsets. So today, we have two more things to show you that are going in exactly that direction, trying to take everything that we've learned from our research and trying to bring them together into a compact form factor that could plausibly get us to visual realism. These are all still prototypes, but they represent pretty meaningful steps towards technology that could one day deliver breakthrough products. So the first one up is an experimental device that brings together some of the latest optics research into a fully functional headset that is unlike anything that exists today. This one we call HoloCake 2. It is the thinnest and lightest VR headset that we've ever built, and it can run any existing PC VR title. In most VR headsets, the lenses are pretty thick, and they have to be positioned a few inches from the display so they can properly focus and direct light directly into your eyes. And this is what gives headsets that look where they're pretty front heavy. But HoloCake 2 introduces two new technologies to get around this. The first one is that instead of sending light through a lens, we send it through a holograph of a lens. And holographs they're basically recordings of what happens when light hits something. So, just like a holograph is much flatter than the thing itself, holographic optics are much flatter than the lenses that they model. But they affect incoming light in pretty much the same way. So it's a pretty neat hack. The second new technology is it uses polarized reflection to reduce the effective distance between the display and the eye. So instead of going from the panel through a lens and then into the eye, light is polarized, so it can be bounced back and forth between reflective surfaces multiple times. And that means that it can travel the same total distance, but in a much more compact package. So the result is this thinner and lighter prototype than any other configuration. But as with anything, when you're building these integrated systems, there are trade-offs and there's a catch. So Michael, you want to take us through that?
Yeah, that catch involves getting the right light source. So HoloCake requires specialized lasers, and that's pretty different from the LEDs that are used in today's VR headsets. And lasers aren't that exotic these days, but they're really not found in a lot of consumer products at the performance, size, and price that you need for consumer VR headsets. So we'll need to do a lot of engineering to achieve a consumer viable laser that meets our specs, that's safe, low cost, and efficient, and that can fit in a slim VR headset. As of today, the jury is still out on finding a suitable laser source, but if that proves tractable, there will be a clear path to sunglasses-like VR displays.
I'm quite optimistic about the direction that all this is heading. A big part of your job, of course, is trying to imagine, all the future technology that we're going to need to solve, and the state of what these technologies will need to be in, 5 to 10 years from now for the multiple generations out of devices that we're building. And I think you have one other design that you wanted to show today. Is that right?
Yep, we have one more design. So ultimately, the goal, obviously, is to bring together all of the technologies we've talked about, integrating all the visual elements needed to pass the Turing test into a lightweight, compact, power-efficient form factor. And we're designing the Mirror Lake prototype right now to take a big step in that direction. So Mirror Lake is a concept design with a ski goggles-like form factor that takes the HoloCake 2 architecture and then adds in nearly all of the advanced visual technologies that we've been incubating over the past 7 years, including varifocal and eye tracking. It shows what a complete next-gen display system could look like. So the key here is that thanks to holography, everything is thin and flat. The varifocal technology is flat, and so are all the holographic films used for HoloCake, as well as prescription correction and eye tracking. And so it's easy to keep adding thin, flat technologies. This means that the end product can pack more functionality into a smaller package than anything that exists today. Now, the Mirror Lake concept is promising, but right now it's only a concept with no fully functional headset yet built to conclusively prove out the architecture. But if it does pan out, it will be a game changer for the VR visual experience.
And I hope that this has given all of you watching today a sense of some of the fundamental challenges in getting to visual realism. Now, one of the reasons why this is such an exciting space to work on is that this is genuinely new technology. Right? We're not just refining the types of screens that we've had on phones or TVs or computer monitors for decades and that already exist. And we have to explore new ground in how physical systems can work together and how our visual system perceives the world. So, I think that augmented, mixed, and virtual reality, that these are going to be fundamentally important technologies. especially for delivering this sense of presence and improving our social interactions. And we're starting to see them come to life, which is really neat. And if we can continue making progress on the kinds of advances that we've talked about here, then I think that that's going to lead to a future where computing is built more around people and how we want to interact with each other and how we want to experience the world. And I think that that's going to be a lot better than anything that we have today. Okay, so that's just about it for me. But if you want to go deeper on all of this, then I recommend sticking around for the rest of the session. Up next, we have Doug Landman from the Display Systems Research Team, which is responsible for all of the prototypes that I showed you today. And I also want to thank Michael for being with us today as well. All right, over to you, Doug.